My name is Sandor Kruk and I'm a research fellow at the European Space Agency. In this presentation, I would like to talk about what happens with the structure of galaxies when you cross a characteristic mass, in particular about the case of something referred to as Boxy peanut bulges. We've already heard a lot in this session about the characteristic masses, at which galaxy properties and physical processes in galaxies change significantly. I'd like to concentrate on the characteristic mass of 3 × 10⁻⁻ solar masses, which was found by Kaufman et al. To be that mass at which galaxies in the local universe transition from having young stellar populations and being disdominated to older stellar populations and higher concentrations typical of bulges. This mass also corresponds to the break in the mass size and mass velocity dispersion relation as found with integral field spectroscopic studies. In this talk, I would like to concentrate on the characteristic mass scales in the context of barred galaxies, like this one, NGC 1300. Barred galaxies are common in our local universe, with up to two-thirds of all spiral galaxies containing a bar. The morphology of barred galaxies arises from the superposition of orbits of stars, gas, and dust in a galaxy, with stars moving along elongated orbits at the center, called X1 orbits, visible here. When looking at barred galaxies edge-on, some appear to have an X shape at the center, which we refer to as a Boxy peanut bulge. This is actually a misnomer, since they've been recognized to be the 3D projection of the bar, which extends vertically above and below the plane of the disk. They have historically been observed in the local edge-on galaxies, such as NGC 1175 here, with about 20 to 40% of edge-on galaxies showing this feature. And if you don't believe me that they look like a peanut, here is an evidence. But going back to them, Boxy peanut bulges are important because there is now strong evidence that our own galaxy, the Milky Way, has a Boxy peanut bulge at the center, albeit with a somewhat weaker X-type signature when looking, for example, at WISE data, here at the center of the Milky Way. So how do such structures form, and what are the properties? N-body simulations suggest that Boxy peanut bulges arise because of a violent vertical instability known as bar buckling, about 1 to 2 giga-years after the bar forms in a galaxy. Bar buckling, visible in the simulation, causes the bar to puff up in the vertical direction, above and below the plane of the disk, as you can see in this simulation here on the right-hand side, and also on edge-on view. You can see slowly the galaxy forming this Boxy peanut shape. And this bar buckling is a type of dynamical instability known as the fire hose instability, which causes thin galaxies with a significant random motion to bend in the direction perpendicular to its long axis, like the water running through this hose. There's an alternative scenario to this, which has been proposed, which is a slower process where stars are trapped in vertical motions, and after a long time gives rise to this structure. How can we identify if barred galaxies have a Boxy peanut bulge? If we look at edge-on galaxies, this is actually difficult, since the bar is not visible. We need to look at face-on or inclined galaxies, like this one. Erwin Debattista, 2003, identifies a new method in which relies on looking at isophot contours of moderately inclined galaxies between 40 and 70 degrees, and with the bar not too close to the major axis of the galaxy. With this particular orientation, the contours of the Boxy peanut project to form a box and 2 spurs offset along the major axis of the rectangle. Preferentially selecting local galaxies with this orientation, they determine the fraction of barred galaxies with Boxy peanut bulges. And this seems to be strongly dependent on stellar mass. Only 20% or less of barred galaxies with masses lower than 10 to the 10.4 have this feature, whereas 80% or more of galaxies with masses bigger than 10 to the 10.5 solar masses contain this feature. And the Milky Way, with a mass of 6 × 10 to the 10 solar masses, would be somewhere here, with a probability of more than 80% of having a Boxy peanut bulge. So perhaps it's not surprising that it has an X-shaped bulge, in fact. The strong distribution gives rise to some questions. What gives rise to it? Is the mass dependence maintained at high redshift? When do Boxy peanut bulges actually form? To answer some of these questions, we looked into data from the Hubble Space Telescope COSMOS survey, which is ideal for high redshift since it covers 2 square degrees, contains a few 100,000 galaxies, and has very good spatial resolution. Pretty much the best you can get right now. For the I-band, and the I-band filter of the ACS camera probes the rest frame optical up to a redshift of 1. To select Borg galaxies to inspect, we use Borg classification from the third version of the Galaxies of Citizen Science project, which asks the members of the public to visually classify galaxies from Hubble into different morphological types, gathering 40 classifications for each galaxy. Since it did not classify Boxy peanut bulges, we used the classification to select a sample of 550 Borg galaxies based on the volunteers' classification to the Borg question. High-redshift datasets suffer from various effects or observational biases, such as degrading resolution, degrading signal to noise because of cosmological dimming, and also band shifting. All these affect the way galaxies appear. We need to account for them if you want to control the observational biases. So we do this by selecting a sample of Borg galaxies from Sloan and matching galaxies individually in stellar mass, in resolution, in Borg properties, and inclination. Finally, to account for the drop in signal to noise, to artificially redshift the local galaxies to the redshift of their pair using the Ferengi code. In a recent paper, we inspected the 550 images of Borg galaxies from Hubble and 550 Borg galaxies of the pairs from Sloan to identify galaxies with and without Boxy peanut bulges. We call the galaxies without Boxy peanut bulges thin bars. And this is based on a resemblance on the isotope contours from N-body simulations. We investigated how the fraction of Boxy peanut bulges evolves with redshift, correcting for observational biases I mentioned earlier, and also for the fact that galaxies were not selected with ideal orientations. We find that the fraction of BP bulges evolves strongly with redshift, from 70–80% locally to basically none at redshift of 1. The first Boxy peanut bulges form around redshift of 0.8, so 7 billion years ago. With the black triangles and green diamonds is shown the fraction of these galaxies that are barred, which seems to follow a similar trend. The first bars appear around the redshift of 1.5, 2, so 9 billion years ago, which suggests there is a time delay of 1 to 2 giga-years between when a bar forms and when it buckles to form a Boxy peanut bulge. So how does the mass dependence change with redshift? We plot here the fraction of BP bulges as a function of stellar mass for 3 redshift bands, and in comparison the values from the previous study of Erwin Debattista. This fraction is not corrected for galaxies having ideal orientations in our sample, which causes the Sloan value with red to be scaled by 50% compared to the value found by Erwin Debattista. But nevertheless, qualitatively the trend is the same. The presence of a BP bulge depends strongly on stellar mass. Looking at high redshift, we find a similar trend. There is a jump here around 10 to the 10.4, 10 to the 10.5 solar masses in the fraction of BP bulges. Fewer galaxies below this threshold have these structures and a lot more above this threshold. This characteristic mass corresponds to 3 times 10 to the 10 solar masses, the same found by other observational studies where galaxy properties and physical processes change significantly. So we can add a new property of galaxies that change at this characteristic mass. That is the formation of Boxy peanut structures that start appearing and dominate the overall population of these galaxies like NGC 1175 here or our Milky Way. And this characteristic mass appears to be the same up to redshift of 1. Okay, so we might wonder what determines the stellar mass dependence and the characteristic mass. What physical property determines the bars in these galaxies to buckle to form Boxy peanut bulges? In the end, the bar doesn't know what is the mass of the galaxy when deciding to buckle or not. But there's no theoretical prediction for the strong mass dependence. It has been suggested, however, for example, that the higher gas fraction can weaken or even suppress the bar buckling. Erwin Debattista looked at the dependence of the presence of a BP bulge with various galaxy properties, such as fraction of gas, Hubble type, color, and bar size. It is complicated since all of these properties scale with stellar mass. Nevertheless, the dependence of stellar mass dominates, and this is the only significant variable between these parameters, as shown in this plot. For the COSMOS dataset, we do not observe secondary correlations either, for example, with bar size. However, we cannot exclude the secondary correlation on gas fraction, since we do not have gas measurements for high redshift galaxies. One possibility could be that the formation of the BP bulge is related to the thickness of galaxies. The thickness of a galaxy is, with respect to its size, is related to the ratio of the vertical to radial velocity dispersion in a galaxy. And this is relevant since the buckling instabilities thought to occur when this ratio crosses a certain threshold. Simulations show that following bar formation, the radius velocity dispersion increases, and this ratio, if it drops below a certain threshold, bar buckling occurs, which increases the velocity dispersion in the vertical direction and causes the galaxy to puff up. Indeed, detailed decompositions of nearby adjunct galaxies performed by Sebastián Comerón suggest that low-mass galaxies have thicker disks compared to high-mass galaxies. And this characteristic mass corresponds to a transition between thick and thin disk domination in galaxies. And higher redshift galaxies are believed to have thicker disks, which could explain the lower fraction of Boxy peanut bulges at high redshift. So in conclusion, we find a strong evolution of BP bulges with redshift from 70% at redshift locally to 0 at redshift of 1. They start emerging 7 billion years ago at redshift of 0.8. The presence of a BP bulge dominates and is primarily and strongly dependent on the stellar mass of a galaxy, with over 80% of massive galaxies like our Milky Way hosting such a structure. This strong mass dependence is maintained for other redshifts as well. So the structure given by the dynamics of stars and galaxies seems to be changing at characteristic mass scales of 3 times 10 to the 10 solar masses. Above this mass, galaxies having thicker bars. As a final thought, it might be possible that the thickness of galaxies could play a role in their formation, bar buckling being suppressed in thicker, hotter disks. But it's an idea that needs to be further explored. Thank you.